And now, welcome to HDPE, the choice for data centers. I am thrilled to welcome back our partners for the sixth consecutive year providing high quality HDPE webinars with ASCE. This session kicks off the 2026 series, and we are proud to have this specific session sponsored by Modern Polymer Pipe and Extrusions, alongside our series sponsors, the Alliance for PE Pipe. Each of the 4 webinars this year will deliver 75 minutes of invaluable content. To get us started, I'll turn things over to your moderator, Peter Dyke, Executive Director for the Alliance for PE Pipe. Welcome, Peter.
Hey, Robin. Thank you. It's great to be back on the channel, and you guys do such a great job. And what a timely topic we have today to share with your audience about data centers. We've got some experts on, and we're going to talk about all things data centers as it relates to pipe, at least from our perspective. So with that, I'd like to introduce Alan Ambler. Alan, why don't you come on and say hello to everybody?
There, Peter. Glad to be here. Great topic, very current and very interesting as well, Peter. I'm glad that our experts were able to share their wisdom and experiences and advance this topic for us.
Yeah, well, Alan, working on this, you and I put this deck together with their help. It's pretty amazing the amount of pipe going into these data centers, and that's where some of the detail that we'll be getting into today. So with that, let's introduce our speakers and get through these first few slides so we can get to the content. All right, so the Alliance for PE Pipe is a trade association. We've got a lot of members that support what we do, and they all believe in education. So we got to take time to say thank you to our members. And oftentimes we're asked about, hey, how do I get training? So McElroy, Strongbridge, George Fisher, and Integrity provide butt fusion and electrofusion training for your contractors and for your teams. And then our distributor population, this group of people these companies have qualified trainers that can produce training for your teams. So that means you have a card that says you're certified minimally competent, that's tongue in cheek, to conduct electrofusion and butt fusions on HDPE, as well as polypropylene. So we're thankful for all these companies that aggressively provide training for your projects. And then we also got to take time to say thank you. A lot of people help us produce this content. So thank you if you're one of those people. And I also wanted to mention that the data today is provided by our experts and our research, and it's generally from publicly available information. Also, our bench today, Dan Landy there on the right is hosting our bench, but we will answer any polyethylene related question that you bring to us. So please use the bench. If you have questions, go to Q&A. And usually on these, we're answering 50 to 75 questions. Andy McElroy, please come on and tell us a little bit about yourself and McElroy Manufacturing.
Thanks, Peter. Happy to be here. Thanks for having me. As you just mentioned, my name's Andy McElroy. I lead business development for McElroy Manufacturing. My sole focus is on mission critical environments. So primarily data centers, but also spend a decent amount of time helping chip fabs, so semiconductor fabrication facilities, and really just trying to grow the fusible market, whether that's underground in the PE or in the building, which is, the polypropylene side as well. So.
All right, Andy, thank you for that. We'll see you in a couple of minutes. Thanks, Michael Harris, welcome from Oklahoma City, Milford.
Yeah, thank you. Thank you for letting me sit on this panel. So I'm Michael Harris. I'm the National Director of Sales. It says VP of Sales there. I'm the National Director of Sales for Milford. I work with all our wind supply brother and sister companies across the United States and helping them understand the fusible space, Peter.
Good. Well, we'll see you in a few minutes, Michael. Thank you for sharing your expertise. And Stephen Boros, a regular provider of content. Stephen, always great to have you on the webinars.
Hey, Peter, thanks. No, always happy to be here. It's always a pleasure to participate in the ASCE webinars that PE Alliance hosts. So it's a great avenue for us, and we seem to get a lot of support through ASCE, and really appreciate being here. Thank you.
So Taylor Holiday is our sponsor. Taylor, welcome back, and thank you for helping us host these webinars.
Yeah, hey Pete, thanks for having us. We're always excited to sponsor these, and nothing especially more than this big topic today of the data centers top of mind and growing the HDPE market. As you know, modern polymers, a manufacturer of HDPE pipe based in Houston, and with offices in Midland and Beaumont. And we always like to work hard with our distributor network, and always want to push for the PE Alliance in any way we can. And we thought, what better way to do it was sponsoring the future of hopefully this HDB pipe world in the data center market.
Well, you're so right. We appreciate your support, and you guys are making great pipe. Keep it up, and let's help us feed these data centers as well as all the other markets across North America, Taylor. So thank you. All right, Andy, come on and tell us. Let's get this kicked off. We're going to start talking about what is a data center. We're going to talk about a little vocabulary, and tell us a little bit more, Andy, about what we're going to hear about today.
Yeah, absolutely. Thanks, Peter. So what I like to do when I have these conversations with whether it's, our industry partners, is kind of level set on what a data center is. I know we read about them every single day, and, good news about them, bad news about them, but what are they? And ultimately they are a big concrete box that has a bunch of computers on them, at the end of the day. What those computers need is land to sit on, power to run them, and cooling to keep them running. And so that's number one. Number two, we're going to look at the market. What are we seeing? What are the hot spots? And where is the place that HDPE and fusibles in general fit? We'll explore what other options are and why fusible is such a good fit here. And then we'll go through a couple case studies with Michael, and then, what's the equipment look like?
Yeah, we get a lot of questions about that equipment, Andy. People want to know, but they understand how the bell and spigot gets together, but they don't really understand about, is a fusion joint stronger than a legacy pipe joint? How does it go together? Why does it go together? Does it lose pressure if you stick it together? That kind of thing. But before we get into too much detail there, Andy, I'd kind of like to go over some of the vocabulary. I learned from you a lot when we produced that podcast that you use a lot of acronyms. For a minute there, I thought you were in the military. And so these acronyms really facilitate conversation, but if you're not familiar with them, it kind of slows things down. Could you give us a quick rundown of some of the vocab?
Yeah, absolutely. And I do try to explain the acronym before I use it or after I use it, but apologies if I don't. These ones right here, I won't read all the way through them, but it is a acronym heavy space. I think just based on the amount of mechanical systems in there. Once you learn them, it does help things. And so, the biggest ones in today that you're going to see is, CDU. This is a coolant distribution unit. This is going to be your secondary cooling network within the facility. And then CRA is a computer room air handler. You'll also see CRAC, which is computer room air conditioner. And then one other that's not on here is HAC, HAC, hot aisle containment. All of these are acronyms that are really focused around how the data center is cooled and differentiating between them.
Yeah, nice. The ones I'm most interested in certainly are HDPE and the PPRCT, and to a lesser extent, the PERT. And one of the things that we're going to be getting into, Andy, is the fact that there really are three separate systems in these data centers. Unlike other conventional, like even a chip fab facility, there seems to be more going on here than in other places. So thank you for putting that together for us. And with that, I'll turn it back over to you.
Awesome. So I did kind of cover this right off the bat, but this is a rendering of what a lot of data centers that are getting built today are going to look like. This is one facility across 4 separate buildings. And as I mentioned, it's going to take up a lot of land. You'll see on the portion of this picture closest to you, those are all generators. So one, they are generally connected to the grid. Increasingly, they are building their own power plants, but their consideration for uptime, and when I mean uptime, I mean keeping it running up as close to 100% of the time as possible, is very important to them. And that's what those generators represent. So if the power goes down, they continue to run. And I will say, one thing that I like to mention on the power is this is one area where a data center can be a a good thing for communities because they can essentially act as a backup supply of power for communities because they consistently need to run these generators to keep them ready, and they push that power back to the grid, which is really just an interesting anecdote. But yeah, we'll move on. So what's driving the demand here? I think it's pretty clear that AI gets used every single day. That acronym is overused, but it is a big driver and an impactful driver of where the demand is coming from. That said, it's not the only reason why we're building more of these. This panel is a perfect example. The backbone of all the internet is living inside of a data center, and everything we do in the digital world relies on them. So I expect that, AI will absolutely drive it, but there is a consistent demand as long as we live in a digital world. This is a good example of by the numbers. This is a JLL Research does a good annual report on what they're seeing in different industries, but here in the data center industry, we see that traditional workload, so what we're using today, is still there, it's still growing, and will continue to move. That said, there is a large impact from AI, and one that will be really interesting to see grow over the next 4 years to 2030. Again, this is once again just showing that we don't see this leveling off anytime soon. And knowing where HDPE and fusibles can fit, it should just look like a big green light for opportunity for our industry. And you'll see that growth measured by gigawatts or megawatts or gigawatts or square footage. They're all just different ways to measure it, but all good trends to help us understand where we're going as a market. The US is, I believe it's the home to the first data center being in Silicon Valley. And we've obviously grown. We have over 5,300 data centers in operation today, and still hold over 50% of the data centers worldwide. But that's not to say that there's not opportunity outside of the United States. We've seen considerable growth throughout Europe and South America. So regardless of where you are in the world, these projects can have an impact for you. And then the US, I would imagine most of the folks here are somewhere on this map. And it's been an interesting change. The hotspot for data centers and where the most densely populated data centers are is in Northern Virginia. What's happened though is they need more land, they need cheaper power, they need more water, and so they've expanded to some secondary and emerging markets. And whether or not you've got a gray, light blue, or dark blue dot in the state that you guys are servicing, the amount of projects that support these mega data center or chip fab projects expands well beyond those dots. This one, I apologize, is a little bit out of place, but once again, just drives home the fact that yes, AI workload is the primary, catalyst for this, but there is still a huge need beyond just AI. And I harp on this, harp's maybe not the right word, but I like to point this out because, everybody talks about the AI bubble, this isn't sustainable. And while there probably is a correction when we figure out what we're going to do with AI, the reality is there is a consistent growing need for things that the data center supports. Here is just kind of speculative. I would guess, since I put this slide in here, that we're trending more towards the right side of this slide than we are the left as far as compounded annual growth rate, which is a great thing. So now that we've kind of covered the market as a whole, what are the systems inside these data centers? So, we talked about the acronyms, and there really are two primary pieces for the cooling side inside of the building, and that is going to be your air-cooled chillers or your evaporative coolers, also referred to as adiabatic or swamp coolers. These are your traditional cooling units that sit on the top of the building and are supplying cold water to essentially a big fan inside that's blowing cold air to dissipate, to remove the hot air. It collects the hot air, takes it back outside. As the workloads in the data centers have increased, so has the heat. And this air to water cooling is no longer sufficient to support the densities within inside these buildings. And so they've added a secondary cooling network, which is you could call a CDU, a coolant distribution unit. They could look a few different ways, but we'll just use the CDU example. And it does essentially redundant of what the air-cooled chillers are doing on top of the roof, but are taking cold liquid in a lot of cases directly to the chip via what's called a cold plate. And they're removing about 60 to 70% of the heat generated by a server directly at the chip level, and then delivering that hot water, making hot air out of it, and basically putting it into a contained aisle to be removed by that, primary legacy system.
So, Andy, as you've developed a lot of these slides and you've spoken all over the country about this kind of thing, we put what you just said into three categories. You got the indoor, outdoor piping. So this is the site work, site development, water from the municipal entity. Then we've got your heat exchange and your server cooling water. Some has glycol, some doesn't. This really helped me better understand the three piping systems. And you're telling me that in the podcast anyway, I learned that we used to have 100,000 square foot data centers. Now, how big are they getting?
Yeah, they're absolutely massive. And the funny thing is they stopped when they didn't stop. It stopped being the primary indicator of how big something is. You don't hear square footage as much. You hear, how much power is it going to use, gigawatts. But you are correct. The average, I'd say 10 years ago, the average data center was going to be 100,000 square feet. Today, if you take the average of all of them under construction, they're definitely above 250,000 square feet, with a lot of the hyperscale gigawatt campuses averaging well into the millions of square feet.
So when you talk about these hyperscalers, you're talking about the companies that have household names, but
Yep.
There's still a lot of people in the real estate business that are doing development work that are building these and then renting them out, right?
Absolutely. Yeah. The traditional, they're called co-locators. These would be the not household names necessarily, the people that were leasing space to, any number of companies. Like McElroy might lease space in a co-locator. The co-locators have turned and look more like the hyperscalers, more like the household name companies, because they have pivoted and started essentially wholesaling to those household name hyperscalers, while also still supporting the colo, but it's less of a focus for them.
So when you use the phrase hyperscaler, are you indeed just talking about them, or are you talking about the co-locators and the hyperscalers?
So I try to not mix them. I can oftentimes, it can refer to both, I guess.
Okay.
But I generally, when I'm referring to hyperscalers, it is the household names, the big tech companies.
Got it. Alan, hit one animation here. I just want to finish this slide. So the purpose, really of this webinar, and the reason Andy and I came up with this was because one of the things that we've learned over time is that the engineering community, some people have strength in plastics and some don't. Some just think PVC is the only pipe there is. And we felt it would be a very good education to better understand what kind of pipe is going in these hyperscaler facilities and how much pipe it is. I was saying to Andy that how excited I was with ISCO on this 70-mile job we did in South Dakota, Andy, and it was 36-inch, 70 miles. Like, that's a big job. But look at what you're doing in these data centers.
Yeah, the amount of pipe going into them is staggering. You'll see here 6 linear feet for every square feet, and that's inside the building. That includes all of the piping systems. A lot of that is chilled water or primary and secondary fluid networks, but it also includes, your standard plumbing and some conduits as well.
Right. One of these images, Michael Harris gave us. Michael's on the call and he's going to contribute. One of the things that we found, and one of the reasons to the audience that I wanted to spend time talking about data centers, is because it's so hard to get information, because a lot of this information is held very close to the vest. but you and Michael Harris and Stephen Boros, you guys have been willing to give us some data so we could put a meaningful deck together.
Yeah, absolutely. And it is, these companies are very protective of their projects. That said, a lot of the information has to be public because the cities that are allowing them to be built have to sign off on it. And that is one nice thing about the size of these is we're given some visibility, even though the owners won't necessarily give it to us.
Right. Well, thank you for talking about that. And as a background to the audience, thank you for listening. All right. So in the category 1, which I call it, which is a great opportunity for HDPE pipe, Andy, is the indoor and outdoor utility. So we're bringing water to the facility. We're handling the site drainage. We're handling natural gas. We're handling sewage. And we're bringing large volumes of water at startup. Tell us a little bit more.
Yeah, absolutely. Water is, as I mentioned, it's one of the top 3 things that these guys care about because they need a lot of it. And yes, they've done a lot of things to get away from the adiabatic, swamp cooler, evaporative cooling because it is a bit wasteful on the water side. But nonetheless, we need a lot of it. And so we're seeing, systems for HDPE be, potable water. It could be for condenser water. And then the one that's really interesting to me, especially if you're in any oil patch across the country, is water coming off of wellheads. And these companies are taking it and, cleaning it so that it can be used within their system. They are that thirsty for water that they're willing to take some of the kind of nastiest water out there and clean it for their applications. Additionally, building power plants on site. That is, a big opportunity for natural gas, and which, as we all know, is a great HDPE fit. We do see other materials, steel, ductile, but what we're seeing, and Michael can speak to this better than I, but we are seeing an incredible increase in the use of HDPE pipe on the underground side, which is a really exciting thing for the fusible industry because it's happening in places that may not have HDPE spec'd for their, municipality, but they're allowing these hyperscalers to do it because they want the projects there.
Yeah, Michael, why don't you come on and just give us some anecdotal conversation about what you've seen and how polyethylene is growing in these municipalities because data centers are showing up in their interest. Yeah.
Yes, you hit it right on the head, Andy. I mean, there's been places where typically when you see bid packages come out, they're not even HDPE is not even added as a optional product or material. And then all of a sudden you have a data center bring this product into their scope. They get it approved, it's spec'd in, and now it opens up the bid process, and now they get added as a option or as a first served material. And that's been very enlightening, and it's one of the things that I've enjoyed seeing, because now when you get in front of some of the city managers, they are very well the projects and they speak highly of HDPE and want to know more.
Well, Michael, one of the things that I've learned over time is that a lot of these tech companies, you look at the Stargate, what Tesla's done, and they've gone totally fusible on a couple of their projects, is they get it because any water loss is no good for them from a sustainability, from an argument standpoint, whereas municipalities still deal with an average of 14% water loss. Michael, what have you seen on that issue?
Yes, so a good point. I was just working down in South Texas last week, Peter, and had a meeting with one of those projects you're speaking about, more about a SpaceX project, and they brought that up as a point of contention, that the reason that they went 100% fusible inside their building there was explicitly no water loss. So now what we're seeing is people are listening because they're gaining all the tax dollars for that business being in their municipalities. And what turns out to see is they're the example of how to reduce the water loss.
Yeah, fantastic story. And I just wish we could write more case studies about this. But anyway, Andy, as far as number one goes, we're seeing evidence that owners are going leak-free, and that's the primary reason they're picking polyethylene, not because they have great experience with it, just because, oh my gosh, here's an opportunity at a facility that requires leak-free, but we can actually do it in the site as well.
Yeah, you're exactly right. And I like to say, these hyperscalers at their core, they're data companies. They are data driven, and that's how they make their decisions. And if you take opinion out of it, which I think some municipalities may have a harder time doing, they see that fusible is the right way to go based on the data. Elimination of leak paths, efficiency of putting it in, cleanliness, no corrosion and scaling. So it's pretty cool to see. So we talked about the underground side. HDPE, the primary player there. As we enter the building, we're seeing really all types of materials. Could be carbon steel, stainless steel, copper, PPRCT, PERT, and some HDPE. These are used in chilled water systems. It could be a glycol focused system. And, these piping systems are the backbone of the cooling network. And then, the heat exchange loop, this is related to our last one, but this is going to be your primary fluid networks. These are running chilled water to your fan walls to essentially remove the heat from your hot contained aisles. They historically have been carbon steel. As we go direct to chip, your options become really stainless steel or a fusible solution. And just anecdotally, this picture is, a publicly posted from the owners, but the construction of these sites is something that we haven't seen before. They are building these projects from the inside out. So this is a indoor piping system that's getting installed before the walls of the building. And I just think it's really cool. It's fast tracking how these are built and the speed to market. And it means that the timeline for the need of pipe is condensed.
Got a great question here. Is polyethylene being used for higher purity water used for humidifiers in some buildings, or are these trending towards other materials?
Can you say that one more time, Peter?
Is polyethylene being used for higher purity water used for humidifiers in some buildings, or are these components trending to other materials when high purity water is a requirement?
High purity water is not necessarily a requirement on the data centers. On the chip fab side, it absolutely is. There's high purity polyethylene and then PVDF that are absolutely necessary in the chip manufacturing process. What I would differentiate, though, is we are seeing fusible on the secondary where the liquid is going directly to the chip. It's not necessarily high purity, but they need cleanliness because they can't have corrosion and scaling getting into the capillaries at the cold plates.
Got it. Thank you.
So as we look through the three primary fusibles, HDPE has the lion's share of the underground side. The PPR plays a little bit there, and then the PERT where the temperature is required as well. The beautiful thing is the fusible market has a solution for really all of the piping needs, whether it's conduit, condensed water, cooler loops. So it's a pretty exciting time to be in the industry.
Yeah, Stephen, why don't you come on? Thank you, Andy. Let's turn this over here for the next couple of slides to our good friend Stephen Boros. Stephen, take it away. Tell us a little bit more about these materials and how they're different from one another.
Hey, Peter. Good afternoon, everyone. Yeah, so Andy kind of set this up really well. So with the multiple systems that you have in these data centers, they each play a different role, and you may or may not need different type of piping for that. What is really interesting is that with the different types of plastic out there, the fusible family has a role. So typically you see the polyethylene, so that's going to bring utilities into the system, and that can be quite large pipe, and it can be bringing water from the source of where it's coming from, wherever that may be, to the data center, and also within the fire loop systems and other systems within the facility, moving large amounts of fluid around. On the higher temperature side, you might see polypropylene PPRCT. We'll talk about each of these a little bit more in a little more detail about what each one is. But that's going to be replacing a lot of the carbon steel. It's easy to fab. It's easy to run inside the buildings. The way it's manufactured, it has much lower thermal expansion and contraction coefficient. So it really limits things that you might be concerned of when putting these mechanical systems inside of a building. Like I said, on the underground side, every data center needs these. You got to connect piping to chillers. You got to bring water to them. You're going to have secondary systems that connect to the CDUs, as we talked about. And then on the mechanical side, that's kind of the differentiator of this inside and outside the building. You're going to have chilled water and heated water. So each material is going to play a different role in that. So as we talked about before, a little more on each material. So polyethylene, what's its main role in these centers? You can see it can be used for a lot of different things. It's not just underground piping, even though that's one of the primary uses of it, but it can move raw or potable water into the systems. I think Andy mentioned sometimes in the oil and gas industry, some of the brine water they're collecting. That's a very corrosive water. You don't want to use anything metallic with those types of fluids. So they're cleaning them up somewhat and then using them for cooling water systems since they have a large amount of it. So there are ways for that, and polyethylene really lends itself well to that. And being a fully fused system makes a monolithic piping system that's not going to leak. It's available in a variety of sizes, 1 inch to 65-inch diameter. So it's readily available no matter what sizes of fluids or what kind of volumes you need to move around. There's standard installation methods already out there, as we all know. I'm using same thing from municipal world that we know already, and it's being used for. All that same stuff can be applied to data centers. So there's a lot of support on that side and for installation and joining practices. Any fittings, headers, anything like that you need for polyethylene is readily available. And of course, the no corrosion means reduced maintenance. PPRCT. Okay, what is it first of all? So polypropylene piping has been around for a long time, but there's several different types of polypropylene piping. So it started out with a homopolymer. Those work okay, but not great. Then you have what's called random copolymers, and that puts in a comonomer of ethylene. And so that's within the backbone structure of the polypropylene. And then this newer technology came up, I don't know, maybe 10 or 15 years ago, maybe a little bit longer, that changed the crystallinity into what we call more the beta phase or a hexagonal phase, to give more of that type of crystallinity. And what they found is that really increases the strength and the temperature resistance of polypropylene. So that opened a whole new realm of being able to use these materials in a lot of HVAC applications. It lends itself perfectly for these data centers environments where the temperatures have to get up to 200, maybe as high as 230 degrees centigrade in these applications. So there's our active standards for that. There's ISO standards. ISO 15874 is a very common one, but we have ASTM standards domestically here in the US as well. F2389 covers all pressure-rated polypropylene piping, including PPRCT. And now there's a brand new standard out there on heat fusion joining of polypropylene, ASTM F3722. So there's a lot of things you can specify as an engineering community out there that's readily available. It's not proprietary. It's industry standard practices, which I believe brings a lot of benefits.
No.
So on the PPRCT side, it's not just the material. So the materials do have PPI ratings, and then they have what's called MRS, or that's under the ISO system for long-term strength rating of their materials. So there are materials listed by PPI, just as there are for polyethylenes and every other types of thermoplastic. So when you get the MRS is typically at 20 degrees C, then you have to do what's called a categorized required stress when you go up to higher temperatures. So you can see these all are long-term stress rated materials to make sure you have that long life in the application. So on the PPRCT side, as I mentioned earlier, it's built a little differently. It's not a monolayer pipe typically. So it's going to be available from 1/2 inch to 24-inch diameter. It can be used up to 200, maybe 230 degrees Fahrenheit, up to 100 psi at those higher temperatures. And so you can see it's actually a multi-layer piping system. You can see the middle layer there. So the inner and outer layer are PPRCT. But the middle layer is actually a glass fiber reinforced layer, And so that glass fiber layer, what its main purpose is not to add more hoop strength to give it more pressure rating capability. It's really to minimize the thermal expansion contraction and expansion of the pipe. So it gives about 1/10, I think, on the amount of thermal expansion contraction that you might see in a non-reinforced polypropylene pipe. So that really helps when you're designing these systems, these mechanical systems inside these large data centers, so you don't get any of those large temperature movements. You can compensate for that, but this material means you don't have to. Then the last material also, so the PERT, polyethylene of raised temperature resistance. It's a semi-crystal material, viscoelastic, just like polyethylene, just like PE 4710. In fact, it is a PE 4710 in all regards. It can be designed the same as 4710, just as our municipal piping is today, same pressure ratings, joining, burial, all that stuff's identical to all the standards we have in place today. But it brings additional temperature resistance, which is really key. Our normal HDPE that we see for municipal applications can be used up to 140 degrees continuous long-term use. PERT can be used up to 180 degrees continual long-term use. So even within data centers, that covers a lot of the heat loop systems that you're looking for, especially when you bring it from the CDU back out to the cooling towers. PERT could be perfect for that. In fact, it is used for that quite often. Again, it's available from 1/2 inch to 24 inch, and it lends itself to a lot of different applications for that. A lot of district heating, district cooling. That's where you see this little niche of PERT really shines.
Yeah, so the difference there, go back to that previous slide, please. Stephen, I have a question. So,
Yeah.
the difference between polyethylene, HDPE, and PERT is in one area, 40 degrees of capability on the warmer water side. How about on the cold water side?
On the cold water side, it's the same. So it's going to be the same as regular polyethylene. So regular HDPE that we use every day, P4710, it can go down to, its brittleness temperature is negative 130 degrees Fahrenheit. So you're not going to have to worry about it on the cold side whatsoever. It still retains ductility.
Yeah, as we get into the other materials, that brittleness really is a key differentiator between HDPE or polyethylene and PVC. Is that correct?
Oh, absolutely. Yeah. You would not want to use PVC in these colder temperature environments typically.
Yeah. One more question for you. You refer to polyethylene as 4710. What does that mean?
So that's the grade of HDPE we use today. So each letter or each number has a meaning. So within the standardization system, ASTM D3350, the 4 means it's high density. The 7 means it's of extremely high slow crack growth resistance. And the 10 is the stress rating of the material in units of 100 PSI. So essentially has a 1,000 PSI long-term hoop stress rating. So that's what all the standards today require to be used for municipal piping applications and industrial piping, FM certified material, firewater systems, all use PE 4710 grade materials today, and they're readily available. The highest level performing, it's really the 4th generation of pressure piping materials for polyethylene.
And how long has it been around?
It's been around now for almost 20 years. So it's not really new, but it's finally been integrated into all the standards and practices that we have today. And it's been refined and improved during that time period. So today, if you use polyethylene 25, 30 years ago, the materials you're using today are 100 times higher performing than they were then.
What is your measurement of performance, or what does that mean?
Well, it's going to be durability and longevity to me. So, any piping system, any material can be a pipe for a certain amount of time, right? If you need it to last a month, you can make it just about anything. If you need it to last 100 years, then it needs to be highly engineered against every failure mechanism we have out there. I wrote a paper for a plastic conference last year that talked about all the failure mechanisms, potential failure mechanisms that could happen with polyethylene, and why we can prove now with today's PE 4710s, we have a true 100-year design life utilizing these materials.
Yeah, and that's pretty theoretical, right? And that's why I was pretty excited to learn that the UKWIR, which is the United Kingdom's version of AWWA, published a paper 3 years ago now, Stephen, where they exhumed first and second generation polyethylene resin. And their calculation was that it was going to last 160 years. It had been in ground for 50 years. They exhumed it, and they said they were going to get a total of 160 years.
Exactly. And that's kind of the difference you see between design life and service life. So they designed those systems 50 years ago to last 50 years. They thought they would. Of course, they expected them to go longer than that. They expect the service life to be longer than the design life, of course. And they're finding out they greatly underestimated even those materials 50 years ago. They're still going to get another 100 years out of them after 50 years of service. And like I said, the materials we use today are 100 times better performing than those.
Yeah, good job. Thank you.
Thanks. All right. So like we talked about the scope and the size. So you got to remember these data centers are going to move around a lot of fluid. So you're going to need large diameter pipe. We're not talking about 1/4-inch diameter, cooling lines here to go to the chips. So underground, you're going to be bringing in maybe up to 42-inch diameter pipe. I think the case study we're going to see later on talks about that a little bit. So you're bringing in massive amounts of fluids potentially, and you're moving them around within the data center. That doesn't mean it's always using that much fluid, because a lot of this stuff is closed loop system after it's already filled and running. The primary fluid network inside could be up to 36-inch diameter, depending on how many data racks or chip racks you have in there. And then you have your secondary fluid network system, which is on your cooling or heating side also, which could be up to 24-inch even. So again, these aren't tiny piping systems. They're pretty rigorous and take a lot of space and a lot of room to put together.
Yeah, and it's kind of exciting because some of the polyethylene's getting used for what PERT could have been used for too, because polyethylene's easier to get than PERT and for that matter, PPRCT. Hey, Andy, before we transition to Dan and talk about competing materials and how the products are differentiated with one another, could you give us, there's this great question here that somebody had, well, which stakeholder is pushing for the use of these plastics, particularly polyethylene? And then also tell us about PPRCT. Is it the civil engineers? Is it the owners, the hyperscalers? Who's doing it? Who's pushing for it?
Great question. And from the hyperscaler side, so we're talking household names, my experience has been that it is the owners, the hyperscalers, that have in-house engineering teams that are making a lot of these decisions that I think historically have been made at the engineering firms. They may still utilize the engineering firms and do, but they are the ones driving a lot of the decision to move towards fusible, which is something that I don't think we've seen in construction at the rate that we're seeing it. They, I think, historically have relied on the engineers, and that's just changing here.
Interesting. Thank you for that. Let's go to Dan Landy. Dan, you put a few slides together so we can talk about all the materials that are being used at data centers, at least in our experience, so the engineers on the call can better understand some of the differentiators of these products. Take it away, Dan Landy.
Yeah, so fortunately, I get to go in the second half of this presentation because we got a lot of great questions. So I'm kind of getting the feel now for what designers are concerned about, with polyethylene. And the way we handle temp and pressure is always going to be a little bit different than other pipe types. So there are competing materials. And I guess the best way to answer this is kind of piggybacking off the questions being asked. And someone asked, when would I use stainless? When would I use ductile? And, I think the question, maybe this might be a little bit arrogant, is when can I not use polyethylene? So the more familiar you're becoming with HDPE and PP RCT, I think you just use it for all those applications, the fusible leak-free product. So we're not going to get specifically into any of those, but we are going to go through some of the characteristics in depth, starting with thermal conductivity. So obviously a lot of materials to pick from. And, Andy got into like the real nitty gritty of each one and kind of the different glycols and mixtures we're going to use with those. So thermal conductivity is basically the ability, how well we're transferring heat through a pipe. So in a lot of instances, we do want thermal and electrical conductivity, but in this situation, we really don't. So plastic pipe is a natural insulator, as Stephen mentioned. So we get additional savings. You don't have to wrap it. There's no sweating and other kind of losses of heat that you're going to get that can accelerate corrosion in metallics. So natural insulator, I think the first application ever for polyethylene was insulating electronics on airplanes in World War II. So it's always been a great insulator. And, that's not always necessarily a design requirement in underground systems, but in these large heat transfer systems, it's really a major benefit. And that's PVC as well. As you can see on that chart, I actually organized this from smallest to largest thermal conductivity. So I think that's one of the main criteria if I was evaluating, the heat losses in these systems. And then corrosion resistance, kind of beating a dead horse, but plastics not going to corrode. Now, my learning curve on this was really interesting. I'm glad we had team meetings and discussing all this because I'm so used to pushing the fact that really long-term usage, corrosion is always going to be a limiting factor. Now, these data centers don't have quite the service life that others are going to have. Are they going to be there for 150, 200 years? Hopefully, maybe they're repurposed into other big box applications. So if you do use polyethylene for your underground activities, it's never going to be a limiting factor for the longevity of this big box, which is, really important. But yeah, metal, obviously you're going to have corrosion. It's going to affect your flow performance and your efficiencies, your pumping costs, etc. That's all kind of a trickle down effect. Now, this I think is a much more appealing case, and it is, all these metallics, they do require corrosion control mechanisms. So without spending too much time on any particular one, zinc coatings, they can be quite expensive. And I'm not picking on ductile iron. I'm not picking on zinc coating. I really like the way Steven put it, of all people. He said that, it's really the simplicity of a plastic pipe solution that we're pushing. We're asking you to use a plastic pipe, HDPE. I know they're going to use some PVC eventually, PP, RCT. We're not really asking you to go above and beyond the actual pipe, right? Our pipe is listed. It is ASTM, NSF, whatever qualifications you guys wanted to, FM. I'm sure there's a lot of FM pipe on these projects. And we don't really need coatings. We don't need cathodic protection. We don't need to control the water. We don't need to balance pH. These are large upfront cost items that just are not associated whatsoever with the total material cost, however you evaluate that. And then protecting pipes from corrosion, without getting too far into the bulk of things. Cathodic protection is a really intricate resource. It's very difficult. It's very expensive. When we do need to use it, once again, we're going to dominate in time, if we're not already, all the applications that polyethylene makes sense, right? But we're never going to get into the really high pressure, the really high temp applications like steel. So yeah, if you can get away with using a metallic, getting into a plastic, it's just going to be a no-brainer. I think the question earlier was asking about stainless steel and ductile, what applications I think that they could compete in. You can use them in these systems, but depending on the longevity and what life you want to have with your pipe, you do have to start considering these coatings, these cathodic protections. And really interesting, Pete, I know you like to talk about this. Controlling water quality. Hard water is a real thing. And are they using processed water? We got a lot of questions about this. Really interesting topic. Are you using processed water? Are you using reclaimed water, potable water? And that depends a lot more on metallics, right? If you're using metallic, you really want to control water quality. With polyethylene, the minerals probably are going to affect efficiency just of the heating and cooling. However, you don't really have to worry about the degradation of the pipe or the effect it's going to have on this flow parameter. So water quality, we basically thread that out the door as well. As long as it's, approved water glycol in the engineering system, we're going to be okay. And then last but not least, balancing pH. Depending on where you are in the country and what your water source is, again, this is going to be a line item that you can just completely throw out the window and not have to concern yourselves with. I know Pete likes to talk about this, but the lead and copper rule. It's the lead and copper rule. Everyone knows it for the lead. And one of the really interesting things about copper is, and I don't even think copper is a bad pipe. It's really great in mechanical systems. This is a large mechanical system, which I think is why copper was maybe an intuitive original thought that people got away from. Copper does struggle in acidic environments, and there's a whole lot of issues associated with that and water quality. But once again, all these are line items that we're just throwing completely out the door when we're considering, going with a smooth wall plastic pressure pipe.
So while Dan's talking about this, Andy, one of the questions that just came in was, does plastic pipe scale in hard water? Do we have any problem, Andy, with scaling of these plastic pipes, which is common in carbon steel and others?
We don't. No, we don't see that type of interaction happening with polypropylene or polyethylene.
Yeah, it's just not a thing for us. Thank you, Dan. Back to you.
And then last but not least, I just challenge everyone to consider overall material costs. So it's kind of maybe counterintuitive that I'm arguing this because we currently are sitting really well in the market in terms of costs. I can't say this for sure, but I believe we're about 20 to 25% cheaper than PVC. But furthermore, when you go into the actual overall material cost, considering maintenance, make sure those are line items you guys are taking into place. The joining methods, HDPE, butt fusion. It kind of seems like a barrier to entry in the municipal marketplace, but when you're comparing it to other materials that promise a leak-free solution, your stainless steels, your steels, etc., those are typically requiring actual welding, which is much more expensive, a much more quality controlled intensive process. So the overall cost of the material, how long am I going to have it there? There's a whole bunch of line items, but joining methods is a major one. And, thank you to our friends at McElroy for pushing out the data log, our destructive testing, and really giving engineers a lot of faith and trust and trackability, I guess, more than anything than we've had in the past. So we're really confident in the solution we have and moving forward. And if anyone does have questions on their specifications for construction, we'd be really keen to helping you guys on those. So reach out anytime. We're happy to help. Thank you.
So Andy, I learned a lot from you in that podcast that we did, and one of the things that I learned is, I like to say in my speakings that we generally have a 12 to 15% market share in municipal water. Yet there are 8 other markets that polyethylene dominates 6 of the 9 markets. PPRCT has a different profile in all these markets. Certainly, they don't compete because they're more expensive. But what are you seeing with acceptance rates compared to the other markets as you've done your work with these data centers?
Yeah, on the underground side, I would say the acceptance rate is well over 60, 70%. I don't have an exact number, but the amount of projects that are switching and that are actively changing designs to HDPE is something we haven't seen at this scale before. On the inside, being the PPRCT, I don't have an exact number for you, but we definitely don't have more than 15% of that market share yet.
Okay, so we're still struggling with market awareness. So good timing on this webinar, right?
Yeah, absolutely.
All right, back to you. Here's opportunity for fusible and some other slides. Andy, take it away.
Awesome. So as I just mentioned, the adoption rate of HDPE and PPRCT is, it's sustainable. The lifespan of it is incredible compared to its metallic alternatives. It's cost effective. And then on the mechanical indoor side, it's lightweight, easy to prefabricate, which lends itself to meeting really tight construction schedules, which is, as many of you may know, a very, very hot topic these days. With the speed at which these are going up, output and throughput have never been more important. That is to say, they've never been more important as long as they're done correctly, which is where the McElroy data logger comes in. This is a device that on a handful of our pieces of equipment actually operate the machine. But on all of our equipment, it can track that a joint was done properly, who it was done by, where it was done, the pressure, temperature over time, essentially saying this joint was done properly and will stand behind whatever warranty that pipe company was offering. And then, as we've kind of talked about, a fusion joint creates a monolithic system. It is taking 2 pieces of pipe and making them one homogeneous piece of pipe, which it equals an elimination of a leak path.
So I just want to go back to the previous slide, please. Andy, I just wanted to clarify, upper left-hand corner, lifespan of 50 plus years. Now, polyethylene is 100 years. PPRCT must then be the 50 years.
So it is 50. That is generally the warranty. It's depending on the manufacturer, they'll offer a 30 to 50-year warranty on their piping system. So we put this slide together. We just said 50 plus, even though we know that it's probably well over 100.
Got it. Thank you.
So I know we've covered a handful of these advantages, but faster to install, less expensive than stainless, One of the interesting ones, especially if you're working with hyperscalers, that they have this image of wanting to choose the green way. Well, surprisingly enough, plastic pipe has a 90% lower embodied carbon than its metallic competitors. And then lastly, the lighter than steel. This is one we haven't talked about as much, and is a really, really good advantage that we have, which is in retrofits, which is taking an old data center and bringing it back, bringing it up to date. They're working with a building that has a load rating of X, and they need to figure out how to maximize the amount of systems that they can get in there. And the lightweight nature of fusible plastics is it can free up that load that could be needed for renovating these projects. So this, before we hit play, this is not my video, obviously, but is a great example of the cooling systems that we've been talking about.
AI is transforming everything from healthcare to self-driving cars to financial services. Across industries, companies are using advanced AI to elevate their business and stay ahead of the competition in ways we never would have thought possible. And the data centers that support these compute and power-intensive AI workloads rely on specialized servers with high-performance processing chips that generate enormous amounts of heat. If the servers get too hot, their performance drops. So that heat has to be managed efficiently, and traditional air cooling methods just aren't gonna cut it. A super efficient way to regulate hardware temperature is with liquid cooling. This method uses pipes to circulate liquid, typically either water or a specialized coolant, to quickly and efficiently absorb heat directly from the equipment. Liquid cooling is effective because liquid conducts more than 3,000 times as much heat as air and requires less energy to do so. That efficiency allows data center operators to stack more servers into fewer racks for higher density arrangements that can meet growing processing demand while saving energy. The most common liquid cooling method for high-power, data-intensive tasks like AI is direct-to-chip cooling. Here's how it works. Chilled cooling liquid starts inside a heat exchanger, which sends it directly to the servers. This cooling fluid flows over metal plates attached right to the processing chips, pulling away the intense heat they generate. Once the heat is absorbed, the liquid flows back to the heat exchanger, where it's cooled and recirculated. But it doesn't stop there. The heat exchanger then transfers this heat to a secondary cooling loop, which rejects it from the building entirely. By combining liquid cooling with an external cooling system, data centers can efficiently manage high-power AI workloads and support next-generation digital services, all while using energy and water resources more sustainably. Now that's progress. To learn more about high-performance data centers and how they operate, check out these other videos.
All right, Andy, so that brings us to tremendous amount of heat. And tell us why rack density matters and how we're dealing with it.
Yeah, absolutely. Great segue. So rack density matters because there is an increased amount of heat that needs to be dissipated. And as we mentioned earlier, air cooling isn't going to cut it. And NVIDIA, as of last month, has announced, some pretty high temperatures at the chip, 45 degrees Celsius. And what that means is that we're going to have to, we as a fusible industry and we as just kind of overall anyone that touches these facilities is going to have to come up with, new ways of removing that heat, knowing that cleanliness matters and speed matters, and efficiency matters. And, fusible is really well positioned to do that. So this 3 kilowatt is the era of maybe the mid 90s. We currently live in the, 50 to 125 kilowatts is a really high density rack. And, it will not surprise me 200 plus be the average in the coming years. So to point the data that points back to that is, today a high density rack is 130 to 250. They talk about 1,000 kilowatts, which is kind of crazy. So there's going to have to be a level step from where we are today and how we cool. And I think that fusibles will be a major player in how that gets solved.
So if go back to the previous slide. So if we're able to handle the Blackwell today, which we are with the thicker wall PPRCT, what does a Rubin mean for us? Can we handle that heat?
Yeah, 45 degrees C is still there. It is at the upper ends of thicker walled PPRCT. It really just depends on the pressure ratings. I have a hard time believing, and I'm not an expert, but I have a hard time believing that average temperatures get much higher than 45 C. I think you have other components within the server that become your weak link that won't allow you to operate any hotter than that, but time will tell.
Got it. Thank you.
So this slide is really meant as an example of what are the 10 largest projects that are announced today. This covers the whole United States. They're kind of scattered across. The average size of these, based on the public data, is 4.2 million square feet. And, the average temperatures that we're seeing are 95 to 113 returned, with a delta of 10 C. And just to put a scale on this, if you take all of the piping systems in the average build here, so in a 4.2 million square foot data center at 6 linear feet or 0.6 linear feet for every square foot, each of these facilities is going to have over 480 miles of pipe. Now that pipe could range from, half inch through, 48 inch. So it's a wide variety, but as far as the need for piping systems, we've never seen this type of demand. And, it should be exciting for anyone in the industry that we have such a good product fit.
Yeah, well done. So that's an average. So that 481 miles, is that in a single build out?
It's in a single build out, but as that, one of my first slides had one campus that had 4 buildings. It likely is not a singular building, but it is across a campus.
Got it. Okay, good job, Andy McElroy. We got 5 minutes left. Michael Harris and Stephen Boros, come on and tell us about this one single project. So Andy gave us a compilation. Now you guys have this single project. Tell us a little bit about this West Texas one.
Sure, Peter. So on this one, at this scale, pipe alone doesn't keep a data center project on schedule. The equipment does. So mostly what I've seen on these jobs is fusion equipment is a critical path in infrastructure. If the machines or the crews aren't ready, everything behind it slows down. So what we're seeing now is owners and contractors locking in the fusion equipment early, right alongside the procurement of the pipe. And Andy hit on it a few minutes ago, but data logging has become a standard. It's no longer being given as an option. It gives owners confidence and makes turnover cleaner. And Peter, when material, equipment, and crews are aligned, fusion actually helps accelerate the project instead of becoming a bottleneck. And that's been a big piece here, why people love the fusion piece.
Yeah, that makes sense. So, tell us a little bit more about what it's like to be you, having to provide the pipe as well as the fusion equipment, Michael.
A good question. So what I've seen and have experienced, and it's been for this old man, it's been enlightening to learn some of the new way of doing things. And AI has changed data centers, or how they're being built. Design and construction are happening at the same time now. It's really impressive. So what I also know is that, let me ground this with a real example. This is an active data center project in West Texas. I can't share the owner or the exact location, but it was a competitive bid, and the pipe size scope is well known. What mattered was who it was what the job required: large diameter underground systems and a schedule that didn't slow down while design were evolving. And that's why owners are pushing so heavily, and the percentage that Andy talked about, the fusible systems and the execution certainty for what fusibles, polypipe, and PP or CT does to keep these jobs on schedule.
Yeah, just to echo that a little bit. So, like Michael was saying, some of these components for these data centers are 12 to 18 months out. That's not the case on the pipe. So polyethylene pipe is one of the components that they can get pretty readily still. They do need some planning for that, but that's the initial stages, right? The first part you're going to do is build all this infrastructure utilizing the polyethylene. That's why it's so important to get it out there and on site and joined early in the design process and the construction process.
Exactly. You hit it right on the head. So that's why, they're making sure that equipment's lined up, because they know how and when to buy fusible pipe.
Tell me a little bit more about the role fabrications play in this. I mean, I get the pipe really well, Stephen, but Michael, I assume you're fabricating some spools that helps out on the job site.
Yes, sir. So every I guess contractor or GC will run their project a little differently. And there's been some cases over in the Abilene area where they would actually buy, rent equipment and our pipe, send it to a location, and we would put technical experts at those locations to help them inspect the fusions along with the data loggers. And they are prefabbing and doing a plug and play to stay ahead of the project, no slowdowns. And that's one of the great things that allows the project to always move and flow on a timely schedule. And Peter, I want to insert right here that another big reason HDPE and polypropylene are so important is that the ability to expand a project later in its growth phase. Tech and how these people are going in, taking a data center that's already existing and moving it along and to its next technology. So what worked 10 years ago is not the technology that's working today. So fusible makes this easy for them, and it allows them to do this in a faster and smoother way, allowing the same space as Andy talked about earlier, that the load is already at its capacity.
Yeah, very cool. Well done. I want to bring Andy on to close. Andy, you only got a minute left, but I did want to provide an opportunity for people to get an understanding of what some of your equipment is. Take it away.
Absolutely. Thanks, Peter. So McElroy is an equipment manufacturer. We have a product ecosystem that includes the data logger, our fusion equipment, and then the vault being where the data of the joint goes. If I could wrap up with one sentence, it would be that, data center owners today care so much that a system was done properly, and McElroy equipment with the ecosystem that is the data logger and vault allow them a point of visibility for QA, QC, and progress that can't be done with any other material or equipment. And it's part of the reason we're seeing such a massive adoption. And yeah, if you'd like to learn more, please feel free to reach out.
Yeah, I haven't seen those tags before, Andy. Those are pretty cool. That shows that, somebody does a fusion and he puts that tag on there so an inspector can come by and not have to even access the data logger. He can just scan that tag.
Yeah, and Peter, it's a great point. That is exactly right. These Vault ID tags will attach. So as soon as you're done with the joint, you take a picture with your data logger, and it uploads all of the data logging information, the joint report, into that QR code. And if anything were out of spec on that fusion, a supervisor is going to get alerted and decide whether or not that joint needs to be cut out and redone.